In the quantum world, particles possess both particle and wave-like characteristics. When the particles are cooled, they act increasingly like waves. They also slow down and their energy decreases. Bosons are particles which are allowed to have the same energy at the same time. For instance, photons, the light particles, and some atoms are bosons. At a sufficiently low temperature, the waves of the bosons overlap, and all of them can be described by a single collective quantum wave. This exotic form of matter is called a Bose Einstein condensate. It was predicted by Albert Einstein and Satyendra Nath Bose nearly 100 years ago, and it took until 1995 to achieve the first experimental Bose Einstein condensate made of alkali atoms. At Aalto University, Finland, researchers have created a condensate of so-called surface plasmon polaritons. These particles are mixtures of light and electron movement in metal nanorods. Unlike most previous Bose-Einstein condensates, this new condensate is formed at room temperature. Let's take a closer look at the surface plasmon polaritons. Tiny rods of metal can be made to resonate along with incoming light. This so-called surface plasmon resonance can be tailored by assembling the nanorods into a periodic array. Light gets trapped between the nanorods, and the light is coupled with the electrons in the metal. This produces a hybrid particle of light and electrons in motion. As an energy source, the researchers use dye molecules placed on top of a gold nanorod array. By exciting the molecules at one end of the array, it is possible to monitor the propagation of the particles that form the condensate. While propagating along the array, the particles meet only molecules that can absorb light. Then the molecules emit light back to the array. Because the molecules vibrate, some energy is lost over each cycle of absorption and emission. This so-called thermalization is seen as a collective shift of the particle population towards smaller energies, that is, from shorter wavelengths to longer wavelengths. When the lowest possible energy in the array is reached, the particles form a Bose-Einstein condensate. This is seen in the energy spectrum as a large number of particles in the lowest energy state, together with thermalized particles at higher energies, as described by the original theory by Bose and Einstein. The condensate shows coherence over distances that are large compared to the case of individual particles. This is analogous to the overlapping waves in atom condensates. The condensate forms in a picosecond, which is 1/1,000,000th of a second. How is it possible to observe something happening so fast? The key is in the experimental setup. By exciting the molecules only at one end of the array, it is possible to observe the light emitted by the forming condensate at each position in the array. Knowing the speed of the particles, the surface plasmon polaritons, the position in the array maps directly into time. This opens a window to the underlying ultrafast dynamics.